Hello everyone, in this video I'm going to show you how to implement a domain coloring program in C. The link will be available in the description, link to the GitHub of the project. Okay, so let's start by including complex.h, mass.h, and a standard IO. So mass.h and the most important one, complex.h. So as the least efficient to implement this project, I'm going to define a 1024 by 1024 matrix, actually 249 by 249 matrix that calculates every value for every cell in the matrix, and then use NetPPM to turn the matrix into a picture. So I'll have a graph by every value in the domain. So let's start. And J, K. A is probably used in complex.h, so I don't want to use that. For I, for J is equal minus 1024. X starts from minus going to plus, and Y starts from plus going to minus. So we have a diagonal move from second place to fourth place of plane, normal plane. J wants to be 1024, J plus plus. For K is equal 1024, K wants to be minus 1024, K minus minus. Printf a floating point number, which is absolute value of the when defining a complex number. Let's define the complex variable. Define z to be j plus k times I. So j is the x and k is the y value. So y value actually. So in order to convert R2 to C1, we need to rewrite a pair xy as x plus y times I. So turning a real plane to a complex plane. Absolute value of z. You may want to appreciate the new line as well. So, in order to turn the matrix into a picture, we need to use NetPBM. So let's define a header for our NetPBM file. So we are going to use P2 2049 to 2049 and a floating point number, which is absolute value of z in its largest amount will be 1024 times radical 2, which is the length at the edge of our plane. So to half, I don't know if the square root is actually complex.h or math.h or not, so I use power of half times 1024. Control X, Control S. Control X, Control S. So, Alt X, V10. Control X2. Control X, so make the graph city graph. Control X, O. Control X, Control S. Graph and new dot C. So let's compile it by GCC new C fast ln vol to new, then new to absolute value, complex absolute value dot ppm. Let's open it to see if it actually works. I use GIMP because other programs don't interpret this kind of NetBPM really well. Open graph absolute value.ppm. Okay. Oh, so we defined a disk with radius of, actually we didn't do that. Something's wrong. Absolute value of z divided by 2. Great. But now the 0 isn't a clear value, so almost all numbers in the range of like -1000, -520 to 0 are almost black. So to make it feel more gradual, let's make a reverse exponential growth, logarithmic growth. So let's do it. So logarithm is included in math.h, so let's use that. Logarithm of 4096 and logarithm of absolute value for this. So Control X, Control S, Control X, O. Open. It is kind of gradual, but the values aren't really that impressive, so let's 12 times logarithm of 496 and 10 times logarithm of complex absolute value of z. Absolutely great. So let's try different expressions, not absolute value only. So in order to do so, first let's have a backup of our values. So let's define this one as color depth. Define color depth as CDP as this value. Let's put in parentheses. Define expression as Control Y as this and only print. Oh no, let's not do that. Let's define expression as z itself and define the color as the absolute value for expression. Yeah, that's right. Okay, so instead of having absolute value of z itself, let's have absolute value of, let's say, z to the power of 5 plus, let's say, and divided by 2 to have a better picture. You know, each pixel is now represents one integer, so we can divide that by 2 to have to zoom it by 2 to the power of 5. Zoom into the graph. Plus, okay, that seems right. Oh, the color depth isn't right, so that would be (420 to the power of 412 to the power of 5). So 512 5 GCC and new caps. By the way, you can see the output here, which is kind of right, but let's see. Okay, so there's a problem here. The only value of z to the power of 5 plus a real number plus a integer, natural number, or any other positive number must be on the minus natural number. So minus fifth root of that natural number, which would be minus 10. That's I. So let's see if we can change it. Okay. J. Control S. Control. Maybe that's not working well, so let's change it to Control S. 4 seconds, that's a lot of time. Now that's a positive number. It should be exact reverse, so let's reverse it. So this one must be from positive to negative and vice versa. K plus plus, J minus minus. Control F. And that's it. So let's add some more details. Let's see if the function is analytic in every place. So it's holomorphic, meaning that it's differentiable if it's differentiable in all places over the graph we are creating. So in order to do that, we need to go for P3, which is, instead of a grayscale feature, it's, let's say it's RGB. It's 3 colors, so we can define our current white as red. So define red to be this value. Now let's define green. As. So in order to see all values are differentiable, we can use arguments. If argument is continuous, we can jump to the conclusion that the function is working. So let's see. Argument of expression times, so the amplitude of our color depth, which is color depth divided by pi. So pi is the highest value for arguments. So if we divide color depth by pi will never have an overflow issue. Let's hope so. Divided by math libraries pi. Let's add green and blue here. Red, green, and 0. We don't have any blue yet. Where am I? Oh. 0.0. 9 seconds, that's awfully slow. But hey, it's fine. Let's zoom in a little bit. 16 color is okay. So yeah, it's working. It has all the zeros well defined, and the green is working, but we could have it better. We could have a more well defined pattern, like not only 5 lines. So let's not divide it by pi to see what happens. We're constantly going to have overflows, but whatever. Okay, let's see if that one worked. Kinda. Oh, so it was once for each 0, and now it's 3.1.4 times. So it's got pi times. We need lots more, so let's make it 10 times. Oh, we are having minus values. Argument can be a minus value. So we have zeros with this cool pattern around them, and we can see it's differentiable all over the place. So all of the green lines are continuous. They don't break anywhere other than around zeros where they are limited by the size of the picture. So zoom out, and yeah, that's it. So let's define blue to something more comprehensible, and it's a little bit too much, so let's divide it by 10 again. Control X, Control C, and let's define blue as red times green divided by a small number, which happens to be 5. And I'm just trying to see which one works the best. And define blue to be printed here. Control X, Control C. Takes 9 seconds to get output into the file.pvm, so caps.pvm, which is too long for a program to take. 12 seconds. Open. So what's going on here? Oh. I guess I don't get what's going on here. So green was okay if it was 10 times this. I don't know what's wrong with blue, so let's turn off green. So blue draws lines for each zero, as you can see. Let's close all the other files. Let's check it again. What's going on? Okay. Let's get our output where green is 10 times, and let's divide it by red so we can have smaller values as we go further in the spectrum. Control X, Control C, Control X, so GCC, and output. So now that's some great one. So yeah, blue is pointing towards zeros, red is controlled by absolute value, and green shows that the function is analytic. That's great. So let's see if we can show other values of it. 512 and complex logarithm of z, and let's define color depth to be like, I don't know, that was good, I guess. Control X, Control C. Let's see how it does. Yeah, it's working. So it's the logarithm function. As you can see, it has the pole here 0 when the value is 512, which we defined in the zoom. So it's technically 1. And that's the 0. The function is continuous everywhere, so the green lines are continuous, and that's it. The program is working. I'll upload it in GitHub and share the link below. Thanks for watching.